Hey guys, today we are going to be doing a means test comparing two different means where the population standard deviations are not known and going over how to classify it as a homoskedastic or a heteroskedastic case. So let's go ahead and read our question. Researchers are doing a study of the mean driving times of different students during an average week. At SUU, a sample of 50 students found that they drive on average 180 minutes per week, with a sample standard deviation of 23 minutes. At USU, a sample of 45 students drive an average of 165 minutes a week, with a sample standard deviation of 18 minutes. Researchers want to see if these mean driving times are the same. Using an alpha of 5%, test the claim, find the critical values, then reject or fail to reject the null hypothesis. Assume the driving times of students during the week is normally distributed, the population variances are not equal to each other, and that the samples are independent from each other. Okay, so the first thing I did was I went through and I wrote down all of the information that I knew, which was our N1 was 50, our sample mean 1 was 180 minutes, and our sample standard deviation 1 was 23 minutes, and that was for our SUU students. And then our N2 was 45, our sample mean was 165 minutes, and our sample standard deviation was 18 minutes, and that was for the USU students. And our alpha is 5%. Okay, and that's all that we know as of right now. So now let's figure out what kind of test we're going to do. So let's go through our flow charts. So first, are these samples independent? Yes, they are, because it said so. Also, students at USU and UVU and SU probably don't impact each other on how much they drive, right? So it would be independent logically that way as well. Are both sample sizes at least 30? Yes, they are 45 and 50. Are the population standard deviations known? No, they are not. We were only given the sample standard deviations. And are both population standard deviations equal? The problem said they were not, so we are going to do a t-test with the usual estimate for standard error. If we wanted to test if the population standard deviations were equal, we would do the chi-squared goodness of fit test, which I demonstrated in my previous video about the homoskedastic cases, but we're not going to do that today. So we're just going to be doing our t-test with our normal estimate for standard error. Okay, because we were able to confirm that it was a heteroskedastic case, which means that the standard deviations are not equal to each other, we have our formula, which was the variance 1 divided by n1 and the variance 2 divided by n2 and the square root of all of that. And then our degrees of freedom is the smaller degree of freedom between the two samples. In our case, it would be 44 because our smallest sample size is 45. Okay. The next thing I did was I calculated the variance, which was the square of the sample standard deviations, and I did that for both of our questions. The next thing we're going to do is we are going to find out what the null and alternative hypotheses are. For our null hypothesis, researchers claim that the population means would be the same. So if they are the same, then that means that if you subtract them from each other, that should equal 0. So our null hypothesis is that mu1 minus mu2 is 0. An alternative hypothesis is the opposite of that, which is mu1 minus mu2 does not equal 0. And since we have an equals and a not equals, then we can determine that this is a two-tailed test. The next thing we're going to do is we are going to calculate our standard error using this formula down here, which was the square root of the variance divided by n1 plus this variance 2 divided by n2, and then the the square root of the entire section. Sorry, I don't know the word. And then you can see that here in my formula where I had the variance divided by n and then the variance 2 divided by n too. And that gives us our standard error of 4.21. The next thing we're going to do is we're going to calculate our t-test statistic, which is our x bar 1 minus x bar 2 minus mu 1 minus mu 2, and then divide that by the standard error. And then the nice thing is that our mu 1 minus mu 2 equals 0 because that's the claim that we are testing, is that mu 1 minus mu 2 equals 0 because we want our two population means to be the same. So that leaves us with x bar 1 minus x bar 2 divided by our standard error. And then that will give us a test statistic of 3.557. The next thing we're going to do is we're going to find our critical values. And so to do that, we have to split our alpha in half to do the two-tailed test. There we go. That will give us an alpha of 0.025. And then we'll plug that into our t, that inverse that 2t. So 0.025 and our degrees of freedom is 44. And that will give us 2.321 and negative 2.321 with a p-value that I calculated of 0.0091. With this p-value and with our t-test statistic, we can reject the null hypothesis. And so why are we rejecting the null hypothesis? Because our test statistic fell into the error, the margin of error, which are the two very ends of the tail. It's the gray shaded in part that we don't want to be in. And then our p-value is also much smaller than our alpha of 5%. Because of that, we reject the null hypothesis, and there's enough evidence to suggest that the means are not equal to each other. Okay, that's all I have for you guys today. I hope you guys have a great day, and good luck on your quiz.